Well, welcome to everyone who's here this morning. Today, we are going to start off with our first speaker, which is Bryan from the Rose-Hulman Institute of Technology, and he will be giving a talk on cruise control.
Do you
So
have
I will
anything
hand it over to him now. Thank you.
Okay, thanks. Can everybody hear me okay? Excellent. Okay, I'm going to start sharing my screen here. There we go. And let me do this. So this is a project that there's material in the Semio textbook that I wrote that supports this project, but this project itself is not in the book. But I'm thinking of writing it up and submitting it to the Semio modeling projects. So it concerns designing a cruise control for a car. And so here's a picture of my car with my bikes on top. It's a 2017 Subaru, and it has cruise control, of course. And one thing I love about it is it has cruise control that can actually apply the brakes. So unlike most cars or old cars where you're going too slow and it applies the throttle, if you go down a hill in this car and it's going too fast, it'll actually apply the brakes too and keep it at a constant speed. So this is a topic that I thought of. I put it in the book, as I said, but I made up a project for my students that they really like, and it's how do you design a cruise control for a car so that it does what you want it to do in a well-behaved fashion. And it's a nice application of the Laplace transform and what's called PID control. So the goal is to keep the car at a desired set speed. And if the car encounters headwinds or uphills, downhill, tailwind, whatever, it'll increase the throttle or increase the brakes to keep the car at the desired speed. How do you design such a system? So now we're going to model the situation with an ODE. It's a simple wind resistance ODE. And many other physical systems are governed by ODEs. And the goal in many cases is to control the system. The whole point of modeling the system is to control it and drive it to some desired behavior, or make the system behave intelligently in the presence of what control people call disturbances: a hill, a headwind, a tailwind. And PID control it's a very common control technique in our technology, and it relies heavily on the Laplace transform. So I really like this as a way to give the students something cool to do with Laplace transforms. So here's the situation. Let's say we're in a perfect world where the road is flat, there's no wind, and we want the car to stay at 25 meters per second. That's about 53 miles an hour. Of course, if you don't have the throttle applied, the car will coast to a halt or an idle. So here's one strategy to keep the car at the speed you want it at. And it's as simple as set the throttle, the cruise control, to maintain the throttle at whatever power is necessary to maintain 25 meters per second. Set it and forget it. This is an example of open loop control. You set the throttle at whatever's necessary to maintain speed, and then it stays there. But the problem is the car will maintain the proper speed as long as nothing happens. But imagine you encounter a headwind or a hill. Well, in order to, it's not going to, open loop control where you set it and forget it is not going to cut it. So to make up a better control algorithm, we need a model for a car. Now I'm going to go for the moment with the simplest possible model where we have linear air resistance. Now you might say, isn't quadratic more realistic? Well, yes, I'll talk about that in a little bit, but let me just go with linear for the moment. The force of air resistance is proportional and opposed to the velocity of the car. If the car has mass m, then Newton's second law, F equals ma, yields that simple differential equation there. And what I'm going to do is I'm going to incorporate a control force. This is under the control of whatever algorithm is driving the cruise control. I call this control force U of t. Now, I model it as an applied force, but in reality, it would be, how much throttle do you apply, how much gas-air mixture goes into the engine. But let's just think of it as very simply, U of t is a force that's under our control. And our goal is to adjust U of t so the car maintains the desired speed. Well, so there you have a simple differential equation at the bottom there. And let's put in some numbers. Suppose the car is 2,000 kilograms, and I picked K to be 40, which comes in units of newtons per meter per second. I actually picked K to be a semi-realistic value for how much power it takes to keep a car at 53 miles an hour, but we don't need to delve into that at the moment. The ODE there, you see there, 2000 V prime equals negative 40 V plus U of T. And if U of T was 0, the car would grind to a halt. So we need to pick U of T. In open loop control, we need to pick U of T so that it maintains the car at the desired 25 meters per second. Well, it's very simple in this case. You say, I want V of T to be identically equal to 25. Substitute that into the ODE here, and look what falls out. V prime is, of course, 0. Negative 40 V of T becomes negative 1,000. And you find that in order to maintain 25 meters per second in this situation, U of T needs to be 1,000 newtons to keep the car at the required velocity. This is the open loop solution. Set the control so that it maintains, sort of applies 1,000 newtons of force to the car. It'll keep it going at 25 meters per second. Now, as I said, that's fine as long as nothing changes. But suppose we're driving along and at time 20 seconds, a headwind pops up and puts an additional 500 Newton force on the car. Well, now our control solution of 1,000 newtons is not sufficient to maintain speed. In this case, the ODE for the velocity of the car becomes what you see there, where h is a Heaviside function. The solution to that is not a constant V of T 25 meters per second. And in fact, it's easy, at this point, it's easy to solve this ODE using Laplace transforms. So this is already good exercise for the students. Suppose you're going, at time 0, you're going the required 25 meters per second, and the headwind pops up. What's the solution going to look like? It looks like this, okay? Everything's going fine up to 20 seconds. The car's maintaining 25 meters per second. Suddenly that headwind pops up and you see the result. You slow down gradually over time, and then you actually end up at, I think it was like 12 meters per second. The headwind drops you down to 12 meters per second. So open loop control is great as long as nothing changes. But things always change, okay? Headwinds, tailwinds, other cars pulling in front of you, hills, etc. Open loop can't adapt to that. These are called disturbances in the lingo of control theory. So as I said, a headwind or a tailwind, you encounter a hill, other cars in the vicinity alter your wind resistance. And if a car pulls in front of you, suddenly you've got less wind resistance. Open loop control will just gleefully charge into the back of the car that's in front of you. So what we need to do is implement some kind of what's called feedback. We need some way to take the speed we're currently moving at and feed it back into the control algorithm and say, too fast or too slow, apply throttle or apply brakes. The question is, as easy as this sounds, it's a little subtle. How do we do that so that the system behaves sensibly? Well, here's what we're going to do. We're going to apply what's called feedback or closed loop control, where the car measures its current velocity, and if it's off target, it'll feed that information back into the control circuit, and the control will say more throttle or more brake. So, and by the way, this kind of control is ubiquitous in all of our technology, not just in cars, not just cruise control, but ignition timing, fuel air mixture, shifting. Everything in modern cars has control theory behind it. In aeronautics, of course, modern aircraft use control algorithms to stabilize the aircraft and augment the pilot input. Some of these aircraft cannot be flown by a human being without the help of a computer. And electronics, essentially all circuits have some kind of control in voltage, current, frequencies. And there's so many other things I could list where control theory is essential to modern technology. So let's look at how we could apply control theory to this cruise control problem. Oh yeah, and I did put this last example I put in the book, vibration control. Some, like in optics labs, optics benches need to be extremely stable when you're doing optical experiments. Sometimes you can't achieve that passively with like rubber dampers and styrofoam or whatever. You need active feedback with accelerometers and actuators to actually control the table vibration. I did put an example of that in the Simio book. Okay, here's a very simple control strategy. It's called proportional control, and it's exactly what the students can be led to think of on their own with very little prompting. It's the kind of thing anybody who knows what's going on would reach for first. If the velocity, I'm going to assume we want to maintain 25 meters per second. If the velocity is lower than 25, tell the car to apply more throttle. If the velocity is greater than 25, apply the brakes. And of course, how vigorously you apply throttle and brakes, well, we'll talk about that. And in fact, we'll talk about it right here. Here's the control strategy. U of t, again, I remind you, is the force exerted by the engine, if you will, according to the control theory, the control algorithm. And the control algorithm says in this red part here, if V of t is less than 25, then U of t will be positive. U of t is a force. If you're going too slow, apply more force. If you're going too fast, if V of t is bigger than 25, U of t goes negative, apply the brakes. K sub p is a constant at our discretion, our disposal. It's called the proportional gain for the system. So it's very simple. It makes perfect sense. It's exactly what you think of doing consciously as a human being. I'm going too slow, more gas. I'm going too fast, more brakes. This doesn't work as well as you might hope. I'll show you. Well, in any case, the controlled ODE, mass times acceleration, equals the force of air resistance here, plus the control force being applied to keep the car at velocity. It becomes that DE you see at the bottom of your screen. Now, when you look at that, we're doing control theory right now. So far, we're still in the realm of first order linear ODEs. This is Calc 2 material in many curriculums. So you could actually do this kind of thing in Calc 2. There's the ODE that governs the velocity of the car. K sub p is a constant we can pick. And so it's interesting to say, let's pick K sub p and see how V of t behaves in this case. So here is an example where I take the ODE and I show you here two examples. The red graph you see here is where there are no disturbances in this, or there are how do I want to say this? There is the blue, I'm sorry, the blue is the original open loop control. The blue is the original open loop control that didn't even come close to maintaining speed. The red is what we get from proportional control, this very simple proportional control scheme. And I chose that proportionality gain to be 1,000, somewhat arbitrarily. You can see how proportional gain behaves. We start off at the speed 25 meters per second, but actually, right out of the gate, proportional control lags, doesn't quite get the job done. It lets the car slow to 24 meters per second, roughly. Even with no disturbances, even when everything is going exactly as planned, proportional control doesn't quite do the job. But as soon as that headwind hits, that 500 Newton headwind hits at time 20, proportional control recognizes it and prevents the speed from dropping below about 23.5 meters per second. Whereas the open loop control that didn't recognize what was going on just lets the car grind down to, as I think I said, 12 meters per second. But here's the part that kind of is surprising to students. That very simple algorithm, we're not going 25, apply more throttle, or we're going too fast, apply more brake, doesn't work as well as you might hope. It lets the car slow to a stable 24 meters per second. And it's easy to analyze, why does that happen? Why can proportional control never give us what we want? Well, it stabilizes at the wrong value, and it always will. And the reason is, if you look at the DE that we're looking at with no headwind whatsoever, so it's mass times acceleration, mv prime, equals force of air resistance plus the control force. If you accept that the solution to that, you can draw a phase line portrait for this ODE and see that it will always stabilize at a constant value. What constant value will it stabilize at? not 25, it'll stabilize at, you can just do the steady state analysis and say, what's the steady state solution? The steady state velocity is what you see there, 25 kp over kp plus k. And if you look at that, lowercase k is always a positive number. So if you examine that expression, it's always less than 25. It's always going to come up short of 25 meters per second. And the only way to get it close to 25 is to take that constant k sub p, that proportional gain, and make it extremely large. But that's undesirable because that results in a very, very jerky control algorithm. The moment anything dips much below 25, the car basically floors it to get to 25, then lets off on the gas, or if you're going too fast, it slams on the brakes to get it to 25 and then lets up. It results in a very harsh control algorithm. So proportional control, as simple as it is, leaves something to be desired. So this leads into the question of how are we going to make proportional control better behaved and hit the target every time? Well, what we do is we throw in what's called an integral term into the control function. So previously, our control function, here it is, kp times 25 minus v of t. We're going to throw another term into u of t, an integral term. It's going to look like this. There's proportional control. Here is what's called proportional integral, or PI control. So ki there is a constant that we get to pick, and the effect that this term here in red has on the control function, the control force, is that if v of t is lagging below 25 consistently over an extended period of time, this integral here will build up and get more and more positive, and that will increase u of t more and more. And the longer the car lags below the desired set speed, the more vigorous the force u of t will become, and the idea is it will, we hope, drive it closer to the desired goal of 25 meters per second. Or conversely, if v of t is too big, it'll apply the brakes more and more vigorously. So the question is, with this control function put into the DE that governs the car's motion, what's it look like? What are we going to get? How are we going to analyze it? Well, so here's what happens. Yeah, that's stuff I already said. Here's what we get when we put that control function into the simple first order ODE that governs the velocity. We end up with, that's the original proportional control. That's a first order linear ODE straight out of DE1, Calc 2. Here's what you get when you throw in that integral control. Now, you look at this, and this is an integral differential equation. And at first blush, you have no idea how to solve that analytically or numerically. What are we going to do with that? How are we going to figure it out? Well, this is the beauty of the Laplace transform. The Laplace transform lays waste to that differential equation because that term in red is very nicely behaved in the Laplace S domain. So you Laplace transform both sides of that equation, and you solve it just as you would solve any ordinary differential equation with Laplace transforms. You Laplace transform into the S domain, put in initial conditions, solve for the Laplace of the unknown function, and then inverse Laplace transform. And it's all easy here because that integral is well behaved when you hit it with the Laplace transform. So here's what it looks like when you hit it with the Laplace transform. Okay, you see on the left, mv prime becomes, there's the Laplace, I use capital V of S for the Laplace transform of the solution of the unknown function v of t. So mv prime Laplaces to this, k times v of t becomes k capital V of S. The blue term there is easy to Laplace transform. And finally, actually, I think I got an extra over S there. And then finally, the red term becomes this. If you use that rule that tells you how to Laplace transform a definite integral from 0 to t. So there's a rule in every Laplace transform table. Look at what happened. The Laplace transform did to that integral differential equation what it does to ordinary differential equations. It's turned it into an algebra problem. So all we got to do now is fill in v of 0, which I'm going to assume is 25, that we're at the proper speed at time 0, solve for capital V of S, and then do the inverse Laplace transform. And the students can easily do this. We use Maple in class. Of course, computer algebra system is a huge help here. So I have the students implement this and solve for capital V of S, and then do the inverse transform. And I omit the gory, I'm not going to do the gory computations, but here's what I did. I took our proportional gain to be 1,000. I took the integral gain to be 500, somewhat arbitrary. I picked something that seemed to work reasonably. And let's see, then I fill in the initial condition, and I put in a 500 Newton headwind at time t equals 20, just to see how this would perform. Anyway, there's the god awful. Oh, I think that 100s, that should be a s squared. I forgot a caret there. Anyway, there's the Laplace transform of this unknown. So now you can Laplace transform, inverse Laplace transform, and get v of t. Oh, I put here v of t. I didn't write out v of t because it's messy, but here's a graph of the results. Open loop control in blue, the original proportional control in red, and proportional integral control in black, PI control in black. And look at what happens. Look at the PI control in black. It starts off at 25 meters per second, and like proportional control in red, it begins to sag a bit. But as the speed stays below the desired 25, that integral term begins to wind up and it increase the throttle and bring it back to 25. And in fact, you can show asymptotically that it will bring it back to 25 meters per second. It will stabilize at the desired value. Now look at what happens at time 20 when that 500 Newton headwind hits. The proportional control in red dips, but recognizes it needs more throttle. It applies it, but it doesn't bring it back to 25. PI control does. It dips and begins applying more throttle and stabilizes it again at 25 meters per second. PI control does exactly what you hoped control theory would do for you in this situation. So this is all a beautiful application of the Laplace transform where they can solve that integral differential equation that otherwise they wouldn't know how to touch. And so some ideas here, some ideas for students to work on that I give out as little projects. PI control, proportional integral control, is usually called PID control. Well, the D is for derivative. You can throw a derivative term into the control function too, and that gives you three parameters: K sub P, proportional gain; K sub I, integral gain; and K sub D, derivative gain, that you can adjust. And there's a whole cottage industry in control theory devoted to how you should adjust those constants to get the desired control. It's called tuning the controller, and there's a whole set of methodologies for doing that. But in this, for their initial introduction, just playing around with it gives them some pretty good insight into it. You might ask, well, shouldn't the model really be quadratic for air resistance? Well, probably. You can apply the PID control theory to that problem as well, but there's one drawback. You can't so easily solve it with the Laplace transform, but you can still do some analysis. You can linearize the v squared term at 25 meters per second. For example, you want to stay close to 25 meters per second, linearize v squared at that point, and then you can apply the linear control theory by linearizing. So that's a great task for students. And of course, the students can explore what happens if I'm going 53 miles an hour. I suddenly decide I want to switch to 70. So you switch the control function to 70. How does the controller respond? And what you'll find is, depending on how you pick those constants, the control gains, the controller may behave badly. For example, it may, if you tell it, I want to go 25 meters per second, it will accelerate to 25 meters per second, and it'll go past it up to 30 meters per second, and then apply the brakes and come down to 26 to 23 meters per second. Then it'll apply the throttle. It'll oscillate about the value and slowly approach it asymptotically as it oscillates. Of course, that's undesirable. A car that just wiggles around the desired set speed, that's undesirable. That will happen if you make poor choices for those control gains. And in fact, and this leads into something I have done once in class, but depending on time, the last point here, that all of this control, this control theory is in some sense best done by going entirely into the Laplace domain using concepts of block diagrams and transfer functions and thinking of the Laplace transform as a function of complex variable. It's not very hard. It makes the analysis and the tuning of the controller and understanding what it's really doing. It makes it somewhat easier. Everything I did here is effectively in all the modeling was in the time domain here. But in the S domain, things get a lot easier, and it gives more motivation for many of our students who have to later take a control theory class to take this stuff seriously and try and understand why the Laplace transform is so useful. So that's my project. Happy to take questions.
That's really cool, Kurt. As someone who was a mechanical engineering student before a mathematician, we didn't do anything fun like that when I was learning Laplace transforms in my ODE class. I was going to ask about the PI integral differential equation. Do you lose anything if you convert that to a second order equation by just taking?
You can. That's what you can also just differentiate the whole thing, make it a second order equation, or in the nonlinear context, you can differentiate it and make it into a second order nonlinear equation. And so that's how they can actually figure out what's the controller going to do. Although you can't really analyze it using S domain techniques, because you can't go gracefully into the S domain then. But you can do things like linearize the V squared and say, okay, what if I stick close to 25 meters per second? And then apply.
And my guess is that in automobiles, they probably do linearize the model.
I don't know. I don't know if I don't even know. I mean, there's so many techniques for control theory. I don't know if they even use PID
anymore, maybe.
My trusty Subaru. I could ask them, but it'll probably be the same as when I ask all other companies, what algorithm do you use? They said, it's none of your business.
Right. Proprietary.
Yeah.
Thank you.
Yeah.
Kurt, I have a Subaru Outback 2015, and very first thing I noticed was, the cruise control slows me down going downhill. So I'm really wanted to hear this explanation. I love it. Thank you.
Oh, you're welcome. Yeah, I realized I didn't know it did that when I got the car and I was driving it home from Bloomington, Indiana, and I had the cruise control set, and then it hit the brakes, and I was like, what the hell's going on here? Something wrong. And then it also has the lane assist, which I didn't know about. They didn't warn me. If you deviate out of the lane, it'll jerk the wheel and bring you back into the lane. That caught me off guard too.
Yeah, I would think so. And that did not happen in 2015.
Yeah, it must have been a new feature in 16 or 17. Also, it emails me. The car sends me an email whenever it's low on wiper fluid. I don't like this Internet of Things. It's creepy.
The lane assist is creepy to me. I had a rental that was doing that. Did not like it.
Oh yeah, you can turn it off, but.
Well, yeah, I was doing that because where I live in St. Louis, there are a lot of lines on the road that don't mean what the car thinks they mean.
Yeah. Well, thanks for coming.
Thank you.
Thank you, Kurt.
You're welcome. See you all around.
Okay.
Thank you so much for that talk, Kurt. Really appreciate it. We will be having another talk starting in just a couple minutes in this room, so feel free to stick around for that. If not, feel free to go to one of the other rooms and hear one of those speakers. We should be getting started presently.
And Kurt, great talk as usual. I am so impressed. We'll be asking for slides. My students will love it.
Happy to provide them. I'm going to write up a semioid project on this too that I'll post up there.
Okay, so this is not a part of the book, right? I was looking.
No, the PID control introductory stuff is in the book, but the specific there I talk about controlling an incubator like you find in a biology lab.
This is also great idea to do integral differential equation. I never did it, and now I think I should start doing it.
Oh yeah, this one is as easy as it gets. Laplace transform solution.
Right. Yeah, this is very good.
Thanks.
Thank you.